I'm going to show you two other ways to do this. So at the end of the day, what does Hess's law do? Hess's law lets you get the enthalpy for a reaction without actually doing it. There are two other ways to do that. The other ways are to use the standard enthalpy of formation method. Very important, especially if you're going to take Chem 102, because very similar formula to get entropy and Gibbs free energy as well. And then there's an average bond dissociation energy method. So let's do this method here. This is method 2 for determining the change in enthalpy for a reaction without actually doing it. You can get the change in enthalpy for a reaction by adding up all the, so this is capital sigma, which in math class means sum, right? Which means add up. By adding up all the standard enthalpies of formation of the products, and then adding up all of the standard enthalpies of formation of the reactants and subtract it. So take the sum of the standard enthalpies of formation of the products, subtract the sum of the standard enthalpies of formation of the reactants, and you get the change in enthalpy for a reaction. So products minus reactants. Where do you find these standard enthalpies of formation? Well, let me show you. You need to find them in the back appendix of your textbook. Now, I've pulled them out in some problems, but let me show you where you would find these things, maybe for a homework, or maybe like take Chem 102 if you need to do these a little more difficult. So again, the link to the textbook is in the syllabus. And once you get into the OpenStax book, when you go to the table of contents, you want to go to the appendices at the back, and it is going to be appendix G. Select standard thermodynamic properties for selected substances. You're going to see that there are 3 columns here in this appendix: the enthalpy column, the change in Gibbs free energy column, and the entropy column. Until Chem 102, you don't want to be looking over here. In Chem 101, you just want to be looking here for standard enthalpies of formation values. And you can see that this appendix is pretty exhaustive. It's got the change in enthalpy of formation values for all kinds of stuff. And it is alphabetical. So if it's not like you just kind of, but you can see it's arranged in some kind of order. Sometimes it's alphabetical by symbol, not letter, which is weird. But you'll find it, hang in there. So anyway, we get some standard enthalpies of formation values. So these are where you find these values, but what are these values? What does the standard enthalpy of formation tell you? Well, what it tells you, folks, is how much enthalpy is going to be released if it's negative, or absorbed if it's positive. So how much enthalpy, how much heat is going to be needed or released to make this substance from its pure elements. So, for example, carbon dioxide. Say I want to know the enthalpy of formation of carbon dioxide. How much energy is needed to create or release carbon? How much energy is needed or released to create 1 carbon dioxide? So how do you make carbon dioxide from the elements? Well, you need carbon and you need oxygen, but you got to remember oxygen is a Brinkelhofer, so elemental oxygen is O2. So to make CO2, you would need 1 C and 1 O2 to make 1 CO2. So if I was to take carbon, pure carbon, and combine it with oxygen, pure oxygen, to create carbon dioxide, if we look up CO2 in that table, and let's say we're in the gas phase, CO2 gas. So if we go down here to carbon and we find CO2 gas, you'll see that that's a negative 393.51. What does that mean? Taking a carbon and an O2 and creating a mole of CO2, that would release 393.51 kilojoules of energy per mole of CO2 that you would create. So that's what that tells you. Okay. It can be positive. So for example, if you want to make HCN from a half an H2, a C, and a half an N2, because you got to remember hydrogen and nitrogen are Brinkelhofers. But if you want to make an HCN, that would require 135.5 kilojoules per mole of energy to make a gaseous CN. Notice that the states of matter are in there. Next thing I want to draw your attention to is that a pure element under standard conditions, which we'll talk about that standard means, is 0. Here's why. These are the enthalpies of formation to create these substances from the pure elements. Well, if you're a pure element, you don't need to be formed, you just come that way. So pure elements in their standard state have an enthalpy of formation of 0. Now, what does that standard mean? That little degree sign up there means 25 degrees Celsius and 1 atmosphere of pressure if you're a gas. So 25 degrees Celsius, that's a little warmer than room temp. So I want you to think, room temp, what would the substance be? Well, at 25 degrees Celsius, aluminum is a solid. So that's why the standard enthalpy of formation for solid aluminum is 0. But at 25 degrees Celsius, aluminum is not naturally a gas. So that's why that value is not 0. That's why that value is that you would actually require, if I want to make gaseous aluminum, I got to put in some energy, right? I would have to melt the aluminum, and then I would have to boil it, right? That's going to take some energy, and that's why it's not shocking that you have a positive value there. If we look up some other elements, you'll find they're all 0 under their standard state. So for example, if we go down and find oxygen, or not, did I just zoom past oxygen? I guess. The heck? There's the oxygen. There we go. Oxygen, O2 gas, 0, right? Phosphorus comes naturally as P4, 0, right? Okay, elements, nitrogen comes as N2. So wherever the heck that is, I don't know where the elemental nitrogen is, but wherever the elemental nitrogen is, 0. Iron comes as a solid, 0. Pure elements, iodine is a Brinkelhofer. It's a solid at room temp, 0. Okay, pure elements have a standard enthalpy of formation of 0. So I've showed you where to find these things. I showed you how they're determined, although you obviously don't have to calculate them. Let's talk about how we can use these to get the change in enthalpy of a reaction without actually doing it. So if we find all those enthalpies of formation for the products, and we find all those enthalpies of formation of the reactants, and we multiply them by their coefficients and add them all up, and we take products minus reactants, we can get the change in enthalpy for a reaction. So let me show you. So let's say I want to get the change in enthalpy for this reaction. So hang on. Let me try to type this bad boy out. Let's say we want to get the change in enthalpy for this reaction. What are we going to do? Well, it is going to be products minus reactants. So we're going to start with the products. So we need the sum. I'm going to use a parentheses. And it's going to be 4 times the standard enthalpy of formation of NO. So when you look up NO in that table and you get 90.37, that's to make 1 molar equivalent of NO. We want to make 4 of them. So that's 4 times 90.37 plus H2O. Well, we need to make 6 of them in the gas phase. So 6 times the H2O, which is negative 241.82. So this is the sum of the standard enthalpies of formation of the products. And now we need to subtract the sum of the standard enthalpies of formation of the reactants. So that's going to be parenthesis 4 times the standard enthalpy formation of ammonia, which is negative 46.19, plus 5 times the standard enthalpy of formation of O2. Well, if you look, I didn't give you O2. There's a reason. O2 is a pure element, so that's 0. So that's plus 5 times 0, which is 0. And now we add these up. And we get negative 904.68. per mole. So if you wanted to do this reaction, if you wanted to have 4 moles of ammonia combined with 5 moles of O2 to make 4 moles of nitrogen monoxide and 6 moles of steam, that would release, that is an exothermic reaction. This is redox reaction here, and that is going to release 904.68 kilojoules per mole of energy. Why don't you give one a shot? So why don't you try this guy? I actually want us to make a prediction here first. So what kind of reaction is this? Well, we got a hydrocarbon in the presence of oxygen making carbon dioxide and water. This is a combustion reaction. Think about combustion reactions. Combustion reactions are reactions that, you know, where you're burning something. Okay, so think about what sign your final answer should probably have. Can you make a prediction here for what should we get, a positive delta H in the end or a negative delta H? And then do it, and we'll talk about it. So go ahead and give this guy a shot. So hopefully you had time there. The change in enthalpy for the reaction is equal to the products minus the reactants. And of course, you got to multiply by the coefficients if they're present. So the first product we have here is CO2. So that's going to be a negative 393.5 plus 2 times 2 equivalents of liquid water. So 2 times negative 241.82. And its products minus the sum of the reactants. So there's the sum of the products minus the sum of the reactants. Methane, negative 74.8 plus, again, oxygen, not listed in the table because it's 2 times 0. So we gonna add this up. Negative 393.5 plus 2 times negative 241.82 minus, the quantity, negative 74.8, which is the same as just adding 74.8, which I now see. So I got a positive, that's not good. See, I know I got the wrong answer. I see what I did. I missed the negative 241. Let's do that again. And now we're going to add 74.8. How about a negative 802.34 kilojoules? I'm not going to nail you on sig figs here. Technically, I guess 10th place, right? Because, addition, subtraction is about the least accurate place value. So 2 of them stop at the 10th place. We're going to stop at the 10th place. Negative 802.3. Let's talk about this. That should make sense. Why should it make sense? We got a negative answer. This is a combustion reaction. I don't know about you. Last time I lit something on fire, it got hot. It gave off heat to the surroundings. And yeah. So if you wanted to take a mole of methane, react with 2 moles of oxygen, and make a mole of carbon dioxide and 2 moles of water, that would release 802.3 kilojoules of energy. Love it. All right. Why is there no change in enthalpy formation for oxygen? Pure element. And or exothermic? Always exothermic, man. Is exothermic.